Alright, we're going to go back to VFDs. So again, this is Mechanical Engineering from Dunwoody, the Circuits and Automation class. So looking at VFDs, these are variable frequency drives. That's what the VFD stands for. So we've looked at some various motors. I think I forgot 2 control motors so far. So we have the DC motor, we can just use a potentiometer to change the speed, right? Put a voltage divider across that. Servo motor, we did this in lab, send it some pulses, it will adjust its position to match that pulse. Stepper motor, we can keep track of how many steps it goes. VFDs are another way to control motors. This type is for an AC motor. And there's back to that AC induction motor that we talked about previously. We showed that video in class. But this is what the VFD will look like in lab. So you can see here there's a few different buttons. There's a start button here. There's a stop button. We can have there's some programming keypad. There's a potentiometer on it as well. So we can use these to start, stop, reverse direction, control speeds for anything on an AC motor like a pump, fan, etc. This can also help save some operating costs, right? We can reduce our energy usage using a VFD. If you have a fan with a fixed speed motor and you want a certain flow rate, you can put a restriction at the inlet, the outlet, or both to control that flow rate. Or we can use a VFD and turn down the speed, not burn as much energy, and that will get us the same flow rate that we need at the outlet. Right? So there's a link there for some standards. This is from Canada, excuse me, and different applications for VFDs and estimated savings. Now, if you have the same thing that needs to be running full speed all the time, a VFD is not going to save you any money. It still might be useful for some other aspects of their controls, but as a money-saving device, not so useful if you don't need any change in that flow rate. So the speed equation for a VFD, this S is our RPMs, so we have 120 times our frequency divided by the number of motor poles. So if I have a 4-pole motor with 60 hertz, typical North American speed, right? So we have 4 times the frequency times 120 over 4, right? So we get 1800 RPM. That would be full speed on that motor. If I give it 30 hertz, what would I get? Well, I put 30 in for this. That gets me 3600 divided by 4, get me 900 RPM. So half speed of 900, 1200. What frequency would that? Well, I could put 1200 here. Divide by that, gets me 10 times 4, gets me 400. So I can back that out and then divide by the 120. What did I screwed that up someplace? No, I got it right. 40, right? So 1200 here, divide both sides by 120, gets me 10 times 4, gets me 40 hertz for that speed, or frequency for that 1200 RPM speed. What can we do with these VFDs? So we can also program a soft start. It's like this S curve. Instead of just ramping right up as fast as we possibly could, we could get this nice soft start. We could have it less elegant. We could have just kind of a ramp rate for that. We can also have an analog control. So right, if I go back to that view that we looked at a little bit ago, there's a potentiometer on there. We can adjust that potentiometer to set the speed directly. And then the other big one is we can integrate with other controllers like a PLC to automatically control the set point on that. So if something is not something is cooling down too fast or not getting enough flow, we can turn the speed up or down accordingly. So as I look back at this guy, right, so that there's some communication ports, we'll deal with that. So there's some notes on here, what's connected. We'll do this in lab in a few days, and it'll be some of the later labs this semester is dealing with the VFD in the PLC lab. So hopefully that makes some sense. We'll talk a little bit more about VFDs and control next time. So stay tuned for that.